Hi, my name is Joe Chacon. I'm an electrical engineer with Padge LLC. This is the 8th of several videos about harmonics, but today's video will not be about harmonics at all. Today I want to talk to you about passive power quality devices used in DC systems. I debated whether to do this video. I decided to do it because DC is making a comeback with large battery storage systems. There are still some that also use DC motors. So I wanted to give you some tools for power quality management on DC systems. I understand the prevalence of 24-volt DC power supplies and their use of passive DC filtering components. I'm really referring to high power applications here, though, and not those common 24-volt DC power supplies or simple power supplies for that matter. Our circuit here is meant to show a 1000-volt pulse width modulated DC system connected to a load that can draw 1000 amps. Let's assume our switching frequency is 8 kilohertz. There is no such thing as a perfectly equipotentially bonded and grounded system, so I introduced some stray capacitance to introduce some common mode noise. Stray capacitance I introduced wasn't that much, but enough to create some common mode noise between my DC and true ground. I also didn't use shielded cable between my PWM source and the load, at least not yet. This is a very realistic circuit you can counter if you're trying to do it cheaply. So Excel let me down because of the complexity of the Fourier transforms, so I had to do the code in MATLAB. It felt like it took me forever to generate the code, so I won't bother you with it, but rather the results. I started using MATLAB in the mid-1990s in college. I stepped away from it for a little bit and then came back to it in grad school. I used it a little bit off and on over the last 20 years. It took me a while to get familiar with it again, but it is like riding a bike. It all came. Okay. Wow. That's a lot of common mode noise, especially at 8 kilohertz, which we said was our PWM switching frequency. That can wreak havoc on our system. It is also a decent amount of differential noise, but not really that bad. Common mode noise is noise that is common to the DC positive and DC negative with respect to ground. Differential noise is truly noise between the DC positive and DC negative. It has nothing to do with a ground reference. Now, check this out. The next thing I did was simply employ shielded cabling and ground my shield at the PWM source. Let's look at how that simple change affects our common mode and differential mode noise, especially our common mode noise. Did you see that? It basically makes our common mode noise negligible. Note, the y-axis is scaled to nanovolts. The differential mode frequency response plot does not change that much. I'd probably stop right here and not do anything else. It's not really required. I emphasize this point strongly here because I've seen applications where shielding was not employed, and you can see the problems that arise. I will go ahead and add a common mode choke just for fun so that you can see what it does to the common mode noise. A common mode choke is modeled schematically like this, and a differential mode choke is modeled schematically like this. Notice the additive flux direction and cancellation flux direction respectively. Here is the plot with the common mode DC choke added. Please note that I did not remove the grounding of the shield at the PWM source. Why would you want to do that? Our common mode choke only reduces the frequency response amplitude by half. If our cables were substantially longer, then you can see where a common mode choke would be necessary. We haven't done anything for a differential noise there. Look at this plot. Let's add that differential DC choke now and see what our differential noise plot looks like. Doesn't really make a ton of improvements, but it does drop our main 8 kilohertz spike from 9 volts down to 7 volts. I could also add something like a snubber circuit to knock out that differential noise. A snubber circuit also works well on common mode chokes too, when you can't seem to filter it all out well. 7 volts at 8 kilohertz for a 1000 volt DC system is more than fine, meaning we don't even need the differential mode choke. I hope it is a bit clearer as to how simple it can be to mitigate noise in a high power DC system. Start with shielding first, then consider the use of a common mode DC choke and differential mode DC choke. You may also need some small snubbers. I hope this knowledge can help you become the DC power quality guru in your company. Please look us up at padge.org. That's padge.org if you need anything on this topic or others.